Hey everybody, welcome back to Linear Algebra Online. So the plan for today is to talk about something called linear transformations, which are, if you can't tell by the name, incredibly vital to the concept of linear algebra. And we've really been studying them all year, and we've been studying properties of them, but basically today I'm just going to formalize a lot of things with them and talk about some really important characteristics of them and stuff like that. So the definition should look pretty similar. So we kind of saw this before in other forms, but now this is the most general way that we can write this. So a linear transformation is just a vector space from a vector space V to a vector space W is just a mapping. We write it this way, T, which then V to W, such that for all the vectors U and V, and then the scalar C, you get these two nice properties. So basically, the transformation on a sum of the vectors is the same as the transformation on each one independently. And basically you can pull scalars out. Honestly, a great way to think about it is just a derivative. A derivative is a linear transformation. It's a linear operator really, but you can represent it with a transformation. And you can take the derivative of a sum or take the derivative of the parts individually and then sum them, right? And you also know that scalars can be pulled out of derivatives and get the same answer, right? And so you can summarize this into one combined statement. Basically says that, again, same setup here. This is a linear transformation if and only if this holds. And this is just doing both those in the same thing. A lot of times you're asked in linear algebra courses to prove that something's a linear transformation, and we will do those kind of things too. But I personally don't like this one, even though that would prove it. I personally just go through each one individually. I think my brain likes it a little bit more. But you can do this too. And what this is really, this is what it says in symbols, but this is geometrically what actually happens in a linear transformation. So basically, a linear transformation is going to take stuff like this and send it to stuff like this. This is 3 Blue 1 Brown does amazing things with this. This is pulled out of one of his videos. But these are basically the important things that have to happen. So the grid lines that you started with, they have to stay evenly spaced, okay? They might be really, really close together now or something. They might be diagonal lines and stuff like that, but they, proportionally to each other, they have to be evenly spaced. You can see that these are not, right? This is nonlinear, even just because the grid lines here get really squished together, whereas here they're farther apart from each other. Another really important point is that the origin needs to stay fixed, okay? You need to be mapping the 0 vector to the 0 vector. You can't map the 0 vector to some other vector. The origin stays fixed, okay? And then they preserve linear combinations. That's, right here. And there's all sorts of nonlinear transformations in math. Honestly, there's probably more of them, I would say. There's a lot of messy things, and the courses to study those transformations are really hard. And it's kind of the same way that there's something called ordinary differential equations, which is your first course in differential equations, and they're nice and kind of straightforward. And then there's these partial differential equations that basically involve partial derivatives, and they get really complicated. And it's the same story in math all the ways through. We're learning the nice things, but there's a whole bunch out there that's the not nice stuff like this. And it's just as important as the nice things. It's just that linear transformations we can utilize for a lot of things too, so we should make sure that we understand them. So just to kind of start off, I think it's good sometimes to see what is not a linear transformation. So that's what I'm going to do here. I'm just going to kind of argue why each one of these is not a linear transformation. So the first one is just a transformation that takes a 2x2 matrix and sends it to the real numbers by taking a determinant. That's how it's going to operate on the 2x2 matrix. So you want to think A is the M 2x2 thing, right? So all you need to do is come up with a counterexample to one of these two things, okay? And there's a lot of ways to do this. This is one way, though. So you could craft a kind of a determinant problem where you can get two different things and contradict the first property of a linear transformation. So if you take the determinant of this sum of matrices, right, if it was a linear transformation, it should equal the determinant of this plus the determinant of this, right? Think derivative again. You should be able to apply the derivative to each one independently. But if we do this out, do the sum out first, okay, we get 1, 0, 0, 1, right? Just the identity matrix, we know that's 1, right? And that is not the same, though. Each of these have a row of a 0, and so their determinants, are going to be 0. So determinant of this thing equals 1, but then it doesn't equal the determinant of 1, 0, 0, 0 plus the determinant of, and I ran out of room. And that's because this thing equals 0, right? 1 doesn't equal 0. So that's like the contradiction. 1 and 0, not the same thing. There's a lot of other ones you can do too. All right, for B, so here we're going to map real numbers to real numbers, and we're going to do it with 2 to the x. So whatever real number I plug in, I just do 2 to that number, and that's my transformation. That is not linear by any means. And this is how you can see it. So you can do 2 to the 1 plus 2, okay? If it was linear, again, it would equal 2 to the 1 plus 2 to the 2. But 2 to the 1 plus 2 is 8, right? And that does not equal 2 to the 1 plus 2 to the 2, which equals 2 plus 4, i.e. 6, right? So this is, failing again the first condition of a linear transformation. The last one actually fails a different condition, okay? So if you want to map real numbers to real numbers by just adding 1 to the vector, that's not going to do it because it's not going to keep the origin fixed, right? If you do t of 0 vector, which is 0, right, you're going to get 0 plus 1, and that equals 1, which is not 0, right? The transformation should send 0 vector to 0 vector, but it's sending it to 1. So that's basically shifting that origin, right, up 1. It's not going to do that important thing where the origin should stay fixed. All right. So these are just some kind of corollaries, you can kind of think about them, to the definition of a linear transformation. And I want to prove the first one. I want to prove that truly the transformation that is linear, operating on the 0 vector, sends it to the 0 vector in the next space. And the power of this is bigger than just thinking the number 0 goes to the number 0. Your spaces can be all sorts of things. You can have a vector space that's like that weird one where addition is multiplication and then multiplication is exponentiation. And that 0 vector was a different kind of thing than the 0 that you're used to, right? It was 1. And we could send that to a 0 vector in polynomial space, which, is a different kind of 0 vector. So this is a very abstract concept. Don't think numbers here, just think concepts. Thinking the thing that acts as a 0 vector is going to the thing that acts like a 0 vector. So to prove A, you can do it pretty quick. So t of 0 vector, right, is equal to t of 0 times v, right, just by properties of vector space, right? And then we know that since, maybe I'll write it in here, since t is linear, right, scalars can be pulled out, And so we can just go and say that's 0 times t of v, right? But t of v is just some, vector. And by properties of, vector spaces, again, 0 times a vector is equal to 0, right? So truly, it's a very short little thing, but that is like the argument, and you would probably want to add some words in there if you were really formally writing it up. But t of the 0 vector is going to go to the 0 vector. That's it. And all these other ones kind of make sense. This is basically just a scalar, right? So you should be able to pull the scalar out. This one is just a different variation on the first property right here. You can just t of u minus v should be t of u minus t of v, right? The property that is by and large the most important and most widely used thing associated with linear transformations is this thing down here. So if you have a linear transformation, it is completely determined by its effect on a basis for v, okay? So what I mean by that is basically this. So this is basically what I mean. If you have a transformation t that sends v to w, and you have a basis that spans v, and then if you do transformation on that basis, the linear transformation on that, the resulting t of v1, t of vn, all that thing acts as a basis for w, which is really nice. Basically, you're not losing information in the transformation, and I'm actually going to formalize that. There's something called the kernel, which we're going to learn about eventually, and the kernel is something I actually used in grad school all the time because I was basically making maps, and I wanted to make sure they preserved certain structures and things, and I basically operated on a basis for a space to make sure that I would know, what kind of space I'm spanning after that. This seems like maybe not a prolific statement, but it's actually pretty powerful, and once you kind of use it, I think, you start to realize how nice it is, okay? And I'm going to try to show it here in this example. So T is a linear transformation that maps R2 to P2, okay? And it does it this way. So T of 1, 1 goes to this quadratic, and T of 2, 3 goes to that quadratic. And I want to find T of negative 1, 2, okay? So what I want you to see first is that a basis for like R2, right, could just be 1, 1 and 2, 3, right? Because they, in two-dimensional space, they're not scalars of each other. So if I want to know what T does to this vector, I can really just figure out what that vector is in terms of this basis, okay? And then do T of that whole thing, and I'll figure out what polynomial I get. So it's another just classic, you could like set up a span matrix thing to do this, but I'm just going to kind of tell you. So, I mean, basically, we have negative 1, 2, right? And we want to know like how much of, I guess I'll call it C1, 1, 1 it takes to get there, and how much of 2, 3 it is to get there. And if you do that out, you'll get that C1 is negative 7, actually, and C2 is 3. And so now, this is like the cool trick. You can just do T of 1, 2, okay? I can really just do T of negative 7, 1, 1, plus 3, 2, 3. And that's just because, that's what negative 1, 2 is in terms of that basis, right, for R2. And this, I don't have to be worried that it's not going to actually map properly to P2. The linear transformation will work nicely with the basis. So now I can just do T of each of these, because it's a linear transformation. 1, 1, plus T of 3 times 2, 3. And then you probably see where this is going. I've got scalars in here, and I can pull those out, right? So I got negative 7 times T of 1, 1. plus 3, I'm just pulling the scalar out, of t times 2, 3. And then now I have it because I have t of 1, 1 and t of 2, 3. And so I can just go and do like, okay, this is negative 7 times 2 minus 3x plus x squared. And then plus 3 times 1 minus x squared. And if you just simplify all that, you're going to get negative 10x squared plus 21x minus 11. So that is what t of negative 1, 2 is. And that all relies on the fact that, of what I was saying down here, a linear transformation is going to be completely determined by its effect on the basis for the, like the domain space, the V there. So that's just kind of a handy trick. So I thought it would be good just kind of sketch out another one of these kind of things. So I'm going to do this one kind of quick with some pausing and things. But so this transformation sends 2 by 2 matrices to R, just given this instruction here. And again, these 2 by 2 matrices are going to be, we've talked about this before. We need 4 basis vectors to describe this space. And these are all linearly independent. You can kind of see it just based on where the zeros are and stuff like that. And so I'm going to do the same thing. I'm going to set up this matrix. So all I'm doing is I'm trying to figure out what combination of these give me this vector. And so if I RREF, I would get this. And so now, now you've got it. So now you know you need negative 2 of these. You need negative 1 of these, 2 of these, and 2 of these, okay? So basically you just do t of 1, 3, 4, 2 is just going to equal, I'll try and color code this, negative 2 of these ones, right? 1, 0, 0, 0. The transformation on that, which is going to be, I want that, negative 2 times 1, right? The transformation on that is 1. So negative 2 times 1, then negative 1 of this transformation, so minus 1 times 2, right? And then, I don't know, the green, 2 of this one, so plus 2 times 3, and then 4 of that one. Nope, sorry, 2 of that one. 2 times 4. And if you are actually good at math, you can do arithmetic, unlike me. But I think if my calculator told me correctly, that's a 10. That's kind of the idea. All I'm doing is I'm basically figuring out where this will end up in the map by 100% relying on the basis for the original space, which I can take to just be these ones in this problem. You can kind of see where a lot of stuff we've done this year starts to connect, because there's a lot of problems out there where you might need to build a basis before you do this kind of thing. And you might need to do like Gram-Schmidt, because you maybe want to build an orthogonal basis. So there are problems out there where I would spend sometimes on the order of like hours just trying to get to a point where I could even do this. And then I would check that my map is actually doing something I wanted to do. Just a lot of connections of stuff we've done this year. Can feel a little overwhelming, I think, when math starts to be so interconnected, but also kind of fun. So take it or leave it. I just want to spend a little bit of time at the end here talking about 2 special linear transformations. One of them is a composition, and the other is going to be a inverse. So a lot of these are pretty intuitive. Both these are. If you have a transformation u to v and another v to w, then you can make the composition of s with t that would send you basically from u to w, right? You go u to v, v to w, and we write it this way. And it's literally just one transformation after another, right? It's the same old, transformation, or same old composition thing that we're sort of used to, and we really do use that same symbol. So I want to prove that if you have these two maps, then the composition is also linear. So each one is linear in itself. Will the composition be linear? And this is actually true for an arbitrary amount of compositions, but you'll see, I think, with the proof how you could just extend it to any amount pretty quickly. So we're just going to go through these two things right here. We just need to check that the transformation on the sum is the sum of the transformations, and that scalars can basically be pulled out of the transformation. Okay, so S composed with T of U plus V, by definition, is just S of T of U plus V. But T is linear, right? So that's going to be the same as S of T of U plus T of V. And then S is linear, so that's the same as S of T of U plus S of T of V. But by definition, right, S of T of U and S of T of V is just S composed with T of U plus S composed with T of V, right? So that actually does the first property there. Then for the scalar one, we just need to make sure that we can pull scalars out of this thing. And so same kind of thing. I'm just going to use the definition first. And then T is linear, right? So I can pull a scalar out of that. And then S is linear, so I can pull a scalar out of that. And then by definition, this thing right here is S composed with T, right? So the scalar has been pulled out of the composition of S and T. So that would do that one. And you could see how if you had arbitrary many of those, you could just extend it really naturally to any amount of compositions and whatnot. The last thing I want to talk about in this video is just the idea of invertible or an inverse transformation. And so if you have a transformation that's linear, it goes V to W, and it's invertible, then there's a transformation T prime. I should say if there's a linear transformation T prime that goes W back to V, such that these two things happen, right? You do T, then T prime, and you get I with the identity with respect to V, and then T prime T, you get the identity with respect to W, then that is what it means to basically have T prime be the inverse of T. So one of the most important things that you want to make sure with checking inverse transformations is domain and ranges all line up. So one thing to check is that if we do like T then T prime and T prime then T, everything will kind of make sense, right? So if we do T composed with T prime, right? The way you can think about this is it's starting here in P1, right? It's going to R2, right? And then, right, so we go here, and then now we're in the domain of T, and we go back to P1. So that checks out, that's good. If we flip things around, we should still kind of start and finish at the same spot. So T starts at R2, and then we map to a linear function. And then we map, so now we're in the domain of T prime, and we go to a R2 kind of vector. And so to check that they're inverses, basically the way you just do that is you just use this, right? And you just kind of crunch through the symbols and hope that you, wherever you plugged in, you end up there, okay? So what this kind of looks like is like if you have T composed with T prime of, say, like U plus Vx, then that T prime operating on that will give you u, and then it'll give you v minus u, right, just based on this instruction. So it'd be t of, u and then v minus u. And then t of u minus u and then v minus u, if you use this, u is the a, so I have a u, b is v minus u, okay? So I have u plus v minus u. And then if you look at what's happening there, right, you go, and there's an x in there, sorry. And then I do u minus u, so I have u plus vx, right, because the u's cancel. And so I have u minus vx. Sorry, plus. It's plus, because you distribute a positive number. And that's good. I started with u plus vx, I ended with u plus vx, so yay. That is doing what it needs to do to be a inverse transformation there. And I won't do it for the sake of time because I think it's probably pretty straightforward, but if you do, you really need to also do t prime composed with t, and this time you just start with like some arbitrary like ab, and you would have to like go through this kind of thing and da-da-da-da-da, and then at the end you better get an ab, and then you can also say yay. This time you can say again, because it happened again. But that's literally what it means to kind of check that something's an inverse. You just show that the transformations, wherever you start with an arbitrary thing, ends at that point. And you really need to do both, because you need both those up there to happen.